Hello everyone, today we are going to understand what is DFS or depth first search. This is basically an algorithm that helps you to go through the entire nodes of a graph. Suppose you have a graph like this one. You are on this one node and you want to go through all the other nodes in this graph somehow. Well, you can use a technique like DFS that helps you do that. There is one more thing like BFS, but that I have already discussed in a different video. So if you want to understand BFS and how the graph works, please check out my other video of graphs and BFS. That video contains everything you will ever need to know about graphs and BFS, and I have provided the link in the description, and you will also see a card somewhere here. Now let us get back to the DFS. So D stands for depth. You can also consider as a path. Depth sometimes confuses people, so you can also consider it as a path. So you can think of it as a path first search. Basically what we do in this kind of algorithm is we will be on any given node, and then from that node we will try to go to other nodes. So suppose I try to go to this node. Then once I'm here on the 2 node, I have choices. I can either go this direction or I can go this direction. So suppose I choose this direction and then I will be on this node. From here I will even go deeper or further in this path. Then I will reach 8, and from here I have a choice to go to 7. So I will go to 7. I will go deeper and deeper in this path. I am traversing a path first. So I'm on 7, and from 7 I can go to 6. So I will go to 6. From here I will go to 4, and from here I will go to 3. And from 3 I have choices. I can go to 2 or I can go to 1. But here is the thing. I have already gone through 1 and I have already gone through 2. It means I cannot go anywhere from this 3. That means I have gone through one complete path in the graph till the end of its depth, and that's why we will now try to go back. So I'm on 3, I will go back. I will be on 4 now. Then from 4 I will go back to 6. Then from 6 I will go back to 7. Then from 7 I will go back to 8. Then from 8 I will go back to 5. Then from 5 I will go back to 2. And here on 2 we had a choice, right? We could go in this direction, but we chose to actually go to this direction, and that's why we actually ended up completing this particular path, right? But we did have choice to go to this side, right? So when we are coming back to 2, we will try to go to other nodes that are connected to 2. So if I try to go to this node, the 3 node, I will see that 3 has already been visited. So it means I cannot go to 3 anymore. It will be like doing the same work again. So I will simply say I cannot go to 3, and I will simply return to 1. Once I come back to the starting node, I will again try to see if this starting node have some other children. Starting node does have a children. It have 3, right? But I cannot go to 3. Why? Because 3 has already been visited. That's why I cannot go to it. So it means 1 does not have any other neighboring nodes that I can go to, and it means I will simply go back from 1 also, and this means the DFS will end at this point. However, if for some reason you actually had a node connected to 1, suppose you had something like this, 10 node is there, then 20 is there, right? Then 11 is there, something like this. Then what will happen is that you will come back from 2. You will see that 3 has already been visited, right? So what you will do is you will go to the 10th node. Then on the 10th node, you will again have a choice in which path you want to go. You can go this path or you can go this path. Suppose you go to this path, so you will reach 20. Now from here you don't have any choices, right? It means there is no neighboring node to 20. So from here you will have to return. You will go back from 20 to 10. And then you will try to traverse the other possibility. So other possibility was 11, right? So I will go to the 11 now. But from here also I don't have any other nodes to go to. So I will simply go back to 10, right? And now on 10, I have no other nodes that are connected to it. Yes, 10 is connected to one node also, but it is the parent, right? It is where it came from, so it will not go back to the parent itself. It will go back to the parent node when everything on this 10th node is done. So here on the 10th node, everything is done. 20 is done, right? 11 is done. So the only option is to go back to the first node and tell that yes, I am done. 10 is done. We are not trying to traverse the first node through 10. We are simply saying that okay, 10th is done. We are closing the DFS for 10 and we are going back to the original node from where we started the DFS for 10. That's all. So here if you look at it properly, what happened is that we picked a node 1 and then we just started going through depth. We took a path And on that path, we just kept on going until that path was completely finished here, right? Then once it was finished, we actually came back. We actually came back till here too. We tried to go to the other direction, but we could not because it was already visited. So we go back to 1 again. Then we try to go through other path, right? On 10th, we had two choices to go through. So we chose to go to the path of 21st. We reached the depth of the 20th path and then we came back. Once we came back, then only we decided to go to the other path, right? That's what a DFS really is. What we are doing in a DFS is that we have a node and then we will have paths, right? So we will take a path and we will go in the depth of that path, complete depth, and then only we will return on that node and then we will take the other path. We will go to the depth of that path, then we will return and then we will go to the depth of the other path. That's what we are doing. And if you really notice it properly, this way of going to a node, going to a path, then returning, then again going to some other path, then returning, there is one algorithm that does this thing very well, which is recursion. So it means that DFS is done mostly based on recursion. If you do not use recursion, the DFS or the graph topic itself will be a nightmare for you. Seriously, guys, it will be truly a nightmare. You will have to deal with a lot of things like maintaining a stack, and all that stuff becomes an extra overhead when you are trying to solve very complicated graph problems. So it becomes very important for us to know and understand recursion very well. Suppose we have this graph and this adjacency list. Now in this adjacency list, I have 0 also, but I don't have any 0 node because this is actually a 1 based graph, right? So we have 1 to 7, but we may need to create an array to store the adjacency list. So in the adjacency list, we will actually have the 0 index, but that 0 index will not actually matter to us because it will not have any neighbors to it. And also none of the other indexes will have 0 as its neighbor also because it does not exist in the graph also. So let us try to see how the DFS will work in this case. We will be on 1. We can be on any other node. We can be on 6 also. But suppose for simplicity's sake, we are on 1. So when we are on 1, we will check its neighbors. We have 2, 4 and 3. So we will start going from left to right in this list because we will be using a loop. So first of all, we will go to 2. And when we are on the 2, I will be on this index. I will use this index to get the adjacency list for this particular 2 node. So the 2 node have 1 in its adjacency list, right? So if I want to go anywhere from 2, I will end up going to 1 because that is the only thing present in the adjacency list here. But we cannot go to 1 from 2 because it has already been visited, right? 1 is where we started from. It means we will need to store it somewhere. So we will have a visited set, and in this set we will store the thing that we have already visited. So I have already visited 1, so I will store it here. And here on the 2, when I'm trying to go through the adjacency list here for 2, I will check if this particular node has already been visited or not. So I will check that in this visited set, and if I found that yes, it has already been visited, I will skip that node. I will not go through that node. But since in the case of 2, there is only 1 here, and I ended up skipping 1, there is nothing else, it means I will simply have to go back. So it means the DFS call for 2 will end on the recursion stack and I will end up going back to 1. Now when I'm on 1 and I have already gone through 2, I will have 4 next on the list. So I will try to go to 4. Now when I'm on 4, I will be able to use this fourth index to access this particular list. So from the fourth also, I will go to the depth. I will keep on going to the depth and depth only. So in the fourth, the first thing we get is 1, right? But we check it in the visited and we find that in the visited we already have 1. We also need to have 2 in the visited because we also visited 2. So 2 will also be there. So since 1 has already been visited, we will skip this thing. We will not call DFS on this. We will go to 5. Is 5 visited? No, it is not visited. So that means we can directly go to the 5th node. I will come here. Then I will use this 5th index to get this latest adjacency list. And when I went from 4 to 5, I will also need to store 4 in my visited. And now at 5, I will try to go through its neighbors. So I see 4 here and I see that 4 is also in the visited. So it means I will skip the 4. Then I will go to 7. 7 is not in the visited. It means I can go to the 7th. Now I am at 7th. It means I can use this index to get the hold of this list. And also when I went from 5 to 7, I will end up storing 5 in my visited set because I have already visited it. So now from the list available for 7, I will see that first thing is 5, but 5 is already visited, so I will not go back to the 5, right? So I will not try to traverse 5 from 7. I will skip it and I will call DFS on the next element, that is 6, because 6 is not visited. So it means I will go from 7 to 6 and now I am at the 6th node. And when I'm going from 7 to 6, I will add 7 in my visited set also. So now I am at 6, right? and I will use this particular list to get a hold of the neighbors connected to this particular node. So I will see that 4 is the first element that is connected to it, right? But I see that 4 has already been visited. It means I will not try to traverse the 4th from 6. I will not call the DFS recursive function on 4 from 6. So I will skip the 4 and I will go to the 7. 7 I see it has already been visited. It means I will not call DFS recursive function on 7 also. So I will skip this one also. And once I skip it, there are no more neighbors. It means we have reached the depth. We have gone through all the elements or all the nodes on a particular path till its entire depth. It means from this point onwards, I will start returning. So the DFS call for 6 will end on the recursion stack, and I will end up going back to 7 automatically. Here also on 7, I have no more nodes to actually go to. I will go out of bound in this list. So it means the DFS on 7 will also finish, and I will go back to 5th automatically from the call stack. Then again from 5, I will go back to 4 because there is no more stuff to go through on 5th node. Then from 4, I will try to go to 6, but I will see that the 6 is already in the visited. I believe I forgot to add 6, so I will add it now. So 6 is in the visited. I will not be able to go here. It means I will directly go back from 4 to 1. So I'm going back from 4 to 1, and then I will be back on this particular list. So I will see that on this list we still have a 3, right? And 3 is also not visited. So I will go from 1 to 3 at this point. And now on the 3 node, I will have access to this list. And in this list, I only have 1, and 1 is already visited. It means I will not call DFS on the first node again. So then I will do whatever I want to do with the 3 node itself, and the DFS will end on the call stack, and I will end up going back to the 1. And once I go back to 1, I will again have this list, right? And in this list, if I try to go any further, I will go out of bound. It means we have gone through all the elements of the first node. So at this point, the DFS will end, simply end. And the code will look like this. First of all, we will have a recursive DFS function that we will create ourselves. That DFS function will have node and will have a visited set. We will need node to actually start traversing, and we will need visited set to make sure that we are not trying to traverse a node that has already been visited earlier. So in this function, the first thing we do is add the node to the visited, so that we will not try to call DFS on this particular node ever again in the future. Now once we have done this, we will simply start doing our work with the current node. So we must have some kind of work with the current node, right? We can either print it, we can calculate something based on the current node. We can do whatever we want with the current node in this section. So right now I'm just printing it. That's what my work is with the current node. Then once I've done my work, I will start going through the next nodes. I will start going through the neighbors of this node. So I will use a for loop to take all the neighbors in the adjacency list of this node. And for all of these neighbors, if they are not in visited, I will actually call DFS on them. I will call DFS on those neighbors. And from this line, a new DFS call will start on the recursion call stack. So we have call stack like this in the computer. Suppose I start from the first node, I will have DFS of 1. Then I go to the node 2 that is connected to the node 1. Then for that also I will have a DFS of 2. Then again I will have a DFS of 3 in the call stack. And suppose that the node 3 is not connected to any other node. It is only connected to 2 node, but we will not call the DFS of 2 from 3 because this line will actually stop us from doing that. It means this for loop will run completely without ever calling DFS on any other thing. So it means after here, this particular DFS call will automatically finish on its own, and hence this instance of DFS function call will be destroyed by the operating system itself, and we will end up going back to this instance, the DFS of 2. And on the DFS of 2, we will again continue with the next neighbor that is present in the adjacency list for node 2. And if there is some other node like 4 connected to 2, then we will have another DFS call stack for 4. In the same way, we will have more call stack. We will keep on deleting call stack and call stack and call stack until we reach back to the DFS of 1. If we have some other nodes, great, we will go for them also. We will create call stack there. Otherwise, this will also be deleted and we will go back to outside. It means the DFS function will end at that point. Now this call stack is not something that we have to maintain. It is maintained by the operating system, the computer itself, because we are using recursion. If you were using something like iterative solution, yes, you will need to maintain a stack yourself. And that's why the entire graph topic and the entire DFS relies heavily on the already provided call stack from the operating system. And that is one of the reasons why we are using recursion so heavily in graph topic. If you don't use recursion, the graph topic will be a nightmare for you, really. Now, one thing I want to point out here is that this part, pretty much this entire part will be common for all kinds of DFS algorithms. But this part, this particular part actually will change. It will change based on what kind of graph you have. Okay. So right now we do have an adjacency list for this particular graph. It means the question is providing us an adjacency list, but it is not guaranteed that you will always have an adjacency list or you will be able to create an adjacency list. Because remember that graph does not mean adjacency list. Graph is a completely different thing. And if you don't understand what a graph is, I will ask you to go through my video of graphs and BFS that I have already made. In that video, I have explained in very detail how you can turn anything like a simple array into a graph or a two-dimensional array like a matrix into a graph. So we do have questions on matrices also. So here is an example where we will not have an adjacency list. We will have to calculate the neighbors of a particular node. So here we have an array of integers. It's a simple array and the ith integer tells the maximum possible jump length we can take from that index. Now, if you do not know how we can generate a graph out of this particular question, you need to watch that video, the graph and BFS video. There you will learn all these kind of things. But I will create it here so that you will understand. So we will have a particular array like 1, 3, 1, 2, 9, 5. And here we have indices like 0, 1, 2, 3, 4, and 5, right? So here this particular number tells you how big of a jump you can make from this position, the 0 position, to any other position. The next positions, actually you cannot go back in this question. So you will have to consider the forward positions only. So 1 means I can make a jump of length 1. So it means at max I can go to 3 here. When I'm on 3, the maximum jump I can make is 3 steps. It means I can either go to 1, I can either go to 2, or I can go to 9, because all of them are within the range of my jump length. Then if I am on 1, I can only make a jump to 2. If I am on 2, I will be able to make a jump on 9, and I will be able to make a jump on 5 also. If I am on 9, I will only be able to make a jump on 5, and if I am on 5, there is nothing else, right? Nothing else to make a jump to. So if I try to create a graph out of it, so I will have a node 1. So 1 will be here, and from 1 I can only go to 3. So I will have an edge from 1 to 3. From 3 I can go to 1, 2, or 9. So I will have 3 edges. That is 1, 2, or 9. Correct? Because there are 3 places that I can go to. And then from this one, I can only go to this 2, right? So I will have an edge from 1 to 2. And then from this 2, I can only go to 9 and 5. So I will have an edge from 2 to 9. And I will have an edge from 2 to 5. Now I believe you can guess what will happen next. We are at 9. So from 9, I can go to 5. So I will have an edge from 9 to 5, right? And from 5 I cannot go anywhere else. So it means I will not have any other edge. Now understand that these edges are actually one way, because we are saying that we can only jump in the forward direction. So it means we will have an edge from 1 to 3 like this, then like this from 3 to 1, then this way, then again this, then this, and here also, and yeah. So what we are saying is that I can go from 9 to 5, but I cannot go from 5 to 9 in the backward direction. Now here is the DFS function that we created earlier. Here also this particular part will actually be the same. You will have a node and you will just keep on adding it in the visited, and you will actually print or basically do whatever work you want to do with the node. But the part that will change is going through the neighbors, because here you do not have an adjacency list, right? ADJ list is not existing here. So it means you will have to calculate what is the next neighbor based on the current node. So you will simply use this jump length rule to calculate the next neighbors. So the way we can use this is we can create a for loop here from 0 to this particular jump length. And jump length is basically what? Jump length is simply this particular node. I'm running a for loop from 0 to this particular node. The node value is like 1, 3, 1, 2, 9. This is going to be the value of node. And in this for loop, what I will do is very simple. I will simply calculate the next neighbor. So neighbor will be node value, okay, plus whatever is the current index. So I will have something like I is equals to 0, right? So I will add I, and that will tell me the next neighbor that I can go to from this particular node. And then I will simply check if NE, that is neighbor, not in visited, then we can run DFS function on this neighbor. And this is how you will be going through the neighbors of this particular graph. So you will have to use the rule provided in the question to figure out what are going to be the neighbors. Now here is another example of two-dimensional grid where you will have to calculate the neighbors again. So we have a 2D grid with m by n dimensions. It means m is the number of rows and n is the number of columns. We can only go up, left, right, and down. So there are only 4 places or 4 directions in which we can go to. Now we have to traverse this entire graph from any node or any cell with the help of DFS. So how can we convert this particular situation into a graph? So we will have a grid like this. Here we have all the coordinates already written in each cell. So it means the middle cell is actually represented as 1 and 1. So we will have a node that will be like a set of coordinates 1 comma 1. It represents the middle cell. Now in order to create a graph from this, suppose we start from this particular node 1 comma 1. So I will have a node 1 comma 1 here, and then I will try to figure out how we can create a graph. So in this problem, we can actually go to these 4 directions: up, left, right, and down, right? So if I try to go up, I will reach 0 comma 1, right? So it means I have an edge from 1 comma 1 to 0 comma 1, because I can reach 0 comma 1 from 1 comma 1. If I try to go down, I will reach 2 comma 1 from 1 comma 1, because it is already allowed. So I will have an edge from 1 comma 1 to 2 comma 1. In a similar way, if I try to go this side, then I will have 1 comma 2. So I have 1 comma 2 also as a node here connected to 1 comma 1. On this side, I will have 1 comma 0. Similarly, here from 0 comma 1, I will have 0 comma 0. On this side, I will have 0 comma 2, because we can go from here to here, right? Then from 0 comma 2, I will again be able to go to 1 comma 2. So I will have an edge from 0 comma 2 to 1 comma 2. Then from 2 comma 1, I will have an edge from 2 comma 2. So okay, I will go from here to here 2 comma 2. Then from 2 comma 2, I can go to 1 comma 2. So I will have an edge between these two nodes. In a similar way, we have 2 comma 0. So 2 comma 0 will be here. I will have a node here. I will have an edge from 2 comma 0 to 2 comma 1, because I can go from here to here or from here to here. And then I will have an edge from 1 comma 0 to 2 comma 2, because I can go here or here. And similarly, we will have an edge from 0 comma 0 to 1 comma 0. So it means we are able to create a graph out of this grid. And now we can take any node and try to run DFS on this. While applying DFS to this grid, this particular part will be the same. The only thing that will change is adding the neighbors. So how do you add the neighbors? Well, suppose you are on 1 comma 1. If you want to go to up, what you will have to do is you will have to subtract 1 from this row number, right? So you subtract, it will become 0. If you want to go in this direction, you will have to add 1 to this column number. That's why it became 2. If you have to go to down, you will have to add 1 to the row number. Similarly, you will have to subtract 1 from the column number to go to the left. So it means to go in 4 direction, you will have something like this. You will have to add negative 1 comma 0 to the current node to go up. You will have to add 1 comma 0 to the current node to go down. You will have to add 0 comma 1 to go to the right direction, and you will have to add 0 comma negative 1 to go to the left direction. So these things will help us to go in different direction from a current node. It means I can store these in a particular set or in a particular map or in a particular array, and I can go through it on a for loop. So I will have a for loop that will go for each direction in directions. So I'm taking one direction from these 4 directions in the direction array, and I'm trying to figure out the neighbor. So neighbor will be equal to node plus dir. Now how you are going to do this node plus dir? Well, that will depend on the particular implementation of your language. You might actually have to take these indices one by one and add them manually, or you might be able to do this with the help of a built-in function, but that's not our consideration here. We are just going to say that yes, we are going to add them just to get the next neighbor. Now once you have the neighbor, you will have to check a few conditions. First of all, you need to make sure that you are not going out of bound. If you are on 2 comma 0 and you try to go this side, there is nothing, right? So you need to make sure that you are not going out of bounds from any node. And for that, we actually have a very long condition. So I will just paste it here. So here's the condition. In this if block, what we are checking is that if the node, the neighbor node, is out of bound, or if it is already present in the visited, we will not go through it again. We will simply continue the loop from here. We will not go any further. We will just skip this iteration and we will continue back from for loop. Otherwise, if it is not out of bound, if it is a valid node like 0 comma 1, and if it is not in visited, then we will go ahead and here we will simply call DFS for this particular neighbor. And here instead of node, we will have neighbor in visited. So if the neighbor in visited, we will simply continue. Otherwise, we will actually go through the DFS. It is a little counterintuitive to check that the neighbor is inside of the visited, because till now we have been checking that it is not in visited. But in this case, it actually makes everything simpler to write in terms of code, because here we are making sure that if the neighbor is actually out of bound or it is already visited, we do not run this thing. We will not run DFS. We will simply continue. Continue means we will directly go for the for loop again. We will skip any of this stuff. So yeah, this is how you will be able to run DFS inside of a grid. So I have poured everything that I know about DFS in this video. So if you like the video and got some value out of it, just like the video, subscribe the channel. If you have some kind of question that you would like me to target, or you have some kind of topic that you would like me to talk about, just let me know in the comments. Now we will meet in the next video. Till then, bye.